There are stars out there that are literally the size of solar systems. The more massive a star is, say 10,000 times the mass of the Sun, the faster it has to burn its fuel to stay balanced against gravity. That means the biggest stars live fast and die young. One of the largest we can actually see with the naked eye is Betelgeuse in Orion. If you placed Betelgeuse where our Sun is, its surface would extend almost out to the orbit of Jupiter, maybe even beyond. Imagine that. The distance from the Sun to Jupiter would be inside the star. It's so enormous that we can see spots on its surface with telescopes from Earth. Betelgeuse is a star near the end of its life, swollen and unstable, though it's not the biggest one we know. Now, we can look so far out into the universe that we can actually see the light from about 380,000 years after the Big Bang, before there were stars or galaxies at all. And in that ancient light, we see patterns that match how galaxies are arranged in the sky today. Where did those patterns come from? The best explanation is a theory called inflation. Inflation says that before the hot, dense state we call the Big Bang, the universe already existed. It was cold, almost empty, but expanding incredibly fast. Then, that expansion slowed down. When it did, the universe heated up, and the particles that would eventually form stars and galaxies came into being. That's the moment we call the Big Bang. Mars and terraforming. Mars is probably the only other planet in our solar system that humans could colonize. It's actually a good candidate. It's got plenty of frozen water beneath the surface and in the ice caps. All the raw materials we'd need to build a civilization are there. We already know how to extract water, split it into oxygen to breathe, and hydrogen for rocket fuel and electricity. So, technologically, we could do it. The only question is when we'll decide to go. Most Mars plans involve sending robots first to build a base, and then humans move in afterward. That's almost certainly how it will happen. Terraforming, changing the atmosphere of Mars to make it more Earth-like, is a long-term goal. There's a place called Hellas Basin, about 9 kilometers deep, where the air pressure is high enough for liquid water to exist briefly on the surface. If we could thicken the atmosphere a bit and warm the planet using greenhouse gases, plants could grow there. They'd release oxygen, and since water's available, you could imagine Mars slowly developing a breathable atmosphere again. It did have one, long ago. Wormholes and time travel. One of the big questions in physics is whether wormholes, those tunnels through space and time, can really exist. Einstein's theory allows for them, but most physicists think they'd be unstable. If you tried to send information or light through, the tunnel would probably collapse instantly. So, time travel through a wormhole is more science fiction than science fact, at least for now. We'll need a proper quantum theory of gravity before we can say for sure. How the Moon formed. The Moon formed around 4.5 billion years ago when a planet about the size of Mars collided with the young Earth. It was a glancing blow that threw debris into orbit, forming a temporary ring, like Saturn's. But that ring quickly clumped together to become the Moon. So, the Moon is made from bits of the early Earth and that other planet mixed together. Could we fly through Jupiter? Number. You could fly through the upper atmosphere of Jupiter, where the gases are thin, but as you go deeper, the pressure and temperature rise enormously. Eventually, anything would be crushed, melted, and destroyed. We don't even know exactly what's at Jupiter's core. Probably exotic stuff like metallic hydrogen. The Juno spacecraft is orbiting Jupiter right now, trying to find out. The multiverse. There's no proof for the multiverse, but it's an idea physicists take seriously. Inflation theory suggests that our universe might just be one bubble among many. Inflation might not stop everywhere at the same time. Some parts of space stop expanding and form universes like ours, while others keep going and eventually form their own Big Bangs. So you end up with a vast collection of bubble universes, maybe even an infinite number. Magnetic fields on planets. Earth and Jupiter have magnetic fields because their metallic cores are still molten and moving. Mars is much smaller, so it cooled faster. Its core solidified, and when that happened, the planet lost its magnetic field. Why the night sky is dark. That's Olbers's paradox. If the universe were infinite and eternal, every direction you looked should end on a star, and the sky should be blazing with light. It isn't, and that tells us something fundamental. The universe has a finite age, about 13.8 billion years, and it's expanding. Light as a particle and a wave. Light behaves both as a wave and as a particle. When we look at how it moves, the math that works best is wave-like. It even shows interference, like water waves. But when we detect it, it comes in little packets called photons. So, light really is both. A particle that moves like a wave. Black holes and Hawking radiation. Einstein's theory predicts that black holes collapse to a single point of infinite density, a singularity. But most physicists think that can't actually happen. Stephen Hawking showed that black holes slowly evaporate by emitting radiation. Quantum theory says empty space isn't really empty. Particles are constantly appearing and disappearing. Near a black hole's event horizon, sometimes one of those particles falls in while the other escapes. The escaping one takes energy from the black hole, which causes the black hole to shrink over time. Eventually, it evaporates completely, returning its energy to the universe. That tells us Einstein's theory breaks down at that point. There has to be a deeper, quantum theory of gravity. Particle physics and hidden dimensions. At the Large Hadron Collider, we create hundreds of millions of particle collisions per second. Most of what we see are just statistical fluctuations, random bumps in the data. But occasionally, something interesting appears. One anomaly, called the diphoton excess, looked like a new, very heavy particle. Over 200 theoretical papers were written trying to explain it. One idea is that it might hint at extra dimensions, tiny, curled-up spaces beyond the three we know. Like a garden hose. From far away it looks one-dimensional, but up close you can see it has a circular dimension wrapped around it. If that's true, the universe could be far more complex than we imagine. Measuring the age of the universe. We measure ages in many independent ways: radioactive dating of rocks, the vibration of the sun, and the life cycles of stars. All the evidence lines up. The Earth is about 4.5 billion years old, the Sun around 4.7 billion, and the universe about 13.8 billion. There was a time, though, in the 1990s, when our data didn't make sense. The universe seemed younger than its oldest stars. Then, in 1998, astronomers discovered the expansion of the universe is accelerating, not slowing down. That solved the puzzle and gave us the modern age estimate. The speed of light. The speed of light isn't just a random number. It's built into the structure of space and time. Einstein showed that the speed of light defines how time and space relate to each other. It's the ultimate cosmic speed limit. Massless particles like photons must move at that speed, while anything with mass can never reach it. That relationship also gives us E equals mc squared. Mass and energy are two forms of the same thing. Is the universe eternal? That's one of the big open questions. Some theories, like those by Hawking and Hartley, suggest any universe that's always expanding must have a beginning. Others think there could be something before the Big Bang, perhaps an eternal framework where universes like ours come and go. We don't know yet, but we might find out soon. Life beyond Earth. There's a real possibility that simple life exists elsewhere in our solar system. Mars may have microbes underground where there's liquid water. Jupiter's moon, Europa, and Saturn's moon, Enceladus, both have oceans beneath their icy crusts, possibly heated by volcanic activity. Even Pluto shows signs of geological activity and hidden water. We've already found thousands of planets orbiting other stars, and we can now study their atmospheres. If we detect gases like oxygen or methane, or something even more exotic, like CFCS, that could be the signature of life or even civilization. Within the next couple of decades, we might actually discover life beyond Earth.